Okay, in this video we're going to look at von Neumann architecture and the fetch, decode, execute cycle as you should learn it if you're studying A-level in computer science. So first of all, von Neumann architecture, what is it? Well, it's a CPU model that was created way back in the 50s, John von Neumann, and it's still useful today as a way of studying a basic way that a CPU interacts with RAM. So over here on the left here we've got a CPU, and here on the right this is RAM, main memory. Now von Neumann architecture, one of the main features of it is that instructions and data are stored together in memory. So here in memory you can see I've got some memory locations, and the first 6 of these have got an instruction in, and where appropriate the instruction and the data for the instruction are stored together. In addition to that, von Neumann architecture, you have registers or specific registers, 6 registers on this model. So we've got the program counter, memory address register, memory data register, and the accumulator. If you'd studied GCSE, then those are the ones that you know about. For A-level, we're also going to introduce the current instruction register and the interrupt register. Each one of these, you can think of them just as a storage location. Storage location to store values. The values might be memory addresses, they might be data, depending on what exactly is happening, but each one of them has a special purpose. In addition to that, we've got some units. So at the bottom here, the arithmetic logic unit, which does arithmetic and logic comparisons. The control unit, which sends control signals, timing signals, and controls the flow of data in the CPU. And the instruction decoder. You may see some models with the instruction decoder as part of the control unit. Doesn't really matter. We've got 3 buses as well: the address bus, the data bus, and the control bus. Control bus is effectively where the signals from the control unit go. I'll mention it once now, but I won't mention it as we go through. Notice that the address bus is one way and the data bus is 2 ways. Okay, so let's go fetch, decode, execute cycle. We'll do a few of these. You'll find that the fetch and execute cycle, or the fetch and execute part of the cycle, are the same all the time, but there are different outcomes for the execute part of the cycle depending on what instruction is being executed, and you do need to know the different executes because it's a common exam question. Just one thing of note here, for the instructions, I'm using the Little Man computer instruction set because that's something that you'd need to study on the course anyway. In reality, of course, these would be instructions in binary, in machine code. We've got the assembly mnemonic version here, but it would be the binary equivalent that was actually stored in memory. Okay, so the fetch part of the cycle, let's begin. So we've got the program counter here, and the program counter stores the memory address of the next instruction to be fetched. So right now we're just at the beginning, so I've just put a 0 in there to map to the first instruction there. So this value would be copied into the MAR, and then the value in the program counter is going to be incremented so that it's pointing to the next instruction to be fetched, in which case it'd be instruction 1, but that's going to happen right after the fetch, decode, execute cycle. So we're not really going to look at the program counter again. The value is 0, is in the memory address register. That's going to travel along the address bus here, and the instructions and data that are in this case memory address 0, are what's being fetched. So they will be fetched along the data bus and will there be stored in the MDR. That completes the fetch part of the cycle. For the decode part of the cycle, this instruction and data combination is copied into the current instruction register. It is then split up into its instruction and its data, or its opcode and its operand. Now the instruction part, the opcode, is sent to the instruction decoder here, and the instruction decoder's job is to just work out what the instruction is and what to do with it. So the CPU will read that instruction, and it'll know that in this case it's a load instruction, and it's programmed that it knows what to do with a load instruction. Okay, so that's it. That's the decode part of the cycle. Now the execute part of the cycle is going to be different depending on the instruction that we're given. In this case, it's a load instruction. So what actually a load instruction does, it's going to get the value that's in memory address 6 here and store it in the accumulator. So it's almost like, for this one, another fetch. It's not another fetch, don't write that in an exam, but it's a bit like another fetch. So here, the 6, the operand 6, is going to be stored in the MAR, because that's a memory address. It'll travel along the address bus. We go to here, find the value here. This time it's just a value, there's no instruction, it's just some data this time. And that's going to come down the data bus and be stored in the MDR. So now we can see the value having the current instruction register as well, because we've still got that instruction stored there. The MDR has got the value in, and it's a load instruction, so all we're going to do is copy that into the accumulator. Okay, that's the end of the execute part of the cycle for that one. Now, in between, before we start the next cycle, what will actually happen is the interrupt register will be checked. It's possible that another task of a higher priority will have arrived at the CPU. And you'll learn about interrupts a little bit later on in one of the software units. But just be to note that in between the execute and the next fetch, this will be checked to see if a higher priority task has come in. And don't worry about it too much, you'll learn more about interrupts later. So the next part of the cycle, we've got the program counter here. It's pointing at address 1. We're going to start the fetch part of the cycle again. So again, it's just going to be exactly the same as it was before. The value in the program counter will be copied across to the MAR. It's going to be incremented here so that it keeps track of what the next instruction is. The next instruction will be 2. The memory address 1 will go along the address bus. We find the instruction and data combination here, sub 7. That's going to come down the data bus into the MDR. That completes the fetch part of the cycle. Decode part of the cycle. We're going to copy the instructions and data into the current instruction register. We'll split it up into its opcode and operand. The instruction or the opcode will be decoded by the instruction decoder, and in this case the CPU knows that it's a subtract function and it's got the programming to deal with that. So execute. So the execute of a subtract function, quite similar to load, and you'll see. So 7 is going to go into the memory address register. It'll travel along the address bus. We find the value that's in 7, in this case it's 12. That'll travel along the data bus and be stored in the MDR. Now it's a subtract function, so basically we're going to subtract whatever's in the MDR and just take it away from the 37. So it's the arithmetic logic unit that does that. So these two values will travel there, the calculation will happen, and the results will be stored here. Of course, 37 minus 12 is 25. That completes that part of the cycle. We check the interrupt register to see if a high priority task has arrived. If it hasn't, we'll just move on. So the fetch part of the cycle. Pointing at index 2, memory address 2, we'll copy that into the MAR, and we'll increment that to be pointed at the 3. 2 goes down the address bus. We've got the instruction there, star 8, it's store 8. That'll come down the data bus, and we'll put it here. And that completes the fetch part of the cycle. We'll then decode, so we'll copy that into the current instruction register, store 8, and split it up into its opcode and operand. The store instruction goes to the instruction decoder. The computer works out that it's a store and it knows what to do with it. Okay, so the store instruction is going to get the value from the accumulator and put it into memory. So it's like an opposite of the load instruction. So how that's going to happen is the 8 will go along the memory address register like this, as before. It finds the memory address 8 there, it's a nice empty one for us. The 25 is going to go into the memory data register. And now you're going to see why the data bus is two-way. Because for a store instruction, the 25 will go this way along the data bus and be stored into memory location 8. That completes the execute part of the cycle. We'll check the interrupt register to see if a high priority task has arrived. Assuming it hasn't, we're on to the next one. So the 3 in the program counter goes along to the memory address register. We'll increment it there. 3 is coming down over here. We've got the instructions here. Branch if positive, branch if 0 or positive to 5. bring that down the data bus. Okay, that completes the fetch part of the cycle. Let's decode. We'll copy it into there. Okay, it's going to split it up into its opcode and operand. The BRP goes to the instruction decoder. We'll work out what to do with it. This time it's a branch instruction. So this is a different instruction, okay? And exam questions often ask you about this one. So branch instruction is also known as a jump instruction. So there's two different names for it, branch or jump. And what it's going to do is compare the value in the accumulator and check if it is 0 or positive. Don't forget the 0 part, if it's 0 or positive. If it is, then the program is going to jump to memory location 5, okay? So in this case, what would happen is the value 25 would go to the ALU and a logic comparison would happen. It would say, is the value greater than or equal to 0? In this case, it is. So we are going to jump. We're going to jump to instruction 5. That means we're going to miss out this instruction here. Okay? So the way that we do that, dead simple, we just change the program counter's value to be 5. Okay, the program counter points to the next instruction. We just make the next instruction 5, thereby skipping out instruction 4. Okay, and then finally what would happen is check the interrupt register to see if a higher priority task is there. Copy this along, increments, go along the address bus, find the instruction is just halt, goes to there, completing fetch, copy it across there, no need to split up the data because it's just an instruction for this one, decode it, and the execute for this is just halt, end the program, that completes it. So I hope you can see that, fetch and execute, fetch and decode, quite simple because it's the same every time, but you do need to know all the different cases for the execute part of the cycle, as that's going to turn your C grade answer into an A grade answer at A level. Good luck, and I'll see you again in another video.